Hello. Today we're going to talk about how to graph rational functions in which the degree of the numerator is greater than the degree of the denominator. You may remember yesterday I talked about the fact that if the degree of f, the numerator, is greater than the degree of the denominator, then there would not be any horizontal asymptotes. What you will have are some other asymptotes that will describe the end behavior of the graph. The first type that can occur is called a slant asymptote. A slant asymptote occurs when the degree of f is one more than the degree of g, f being the numerator, g being the denominator. To find the slant asymptote, you actually divide f of x by g of x, find the quotient of that, which will be a line in the form y equals mx plus b, and you ignore the remainder. And I'll talk about in a moment why that is the case. I'll give you a second to write that down. Okay, let's look at this first example here. This is on your third page of your graphs there that I gave you, the one at the very bottom. F of x equals x squared minus 9 divided by x. Now, like we said, this is not going to have a horizontal asymptote because this degree of the numerator is greater than the degree of the denominator. So what we are going to look for is what's called a slant asymptote. And like we said, that occurs when this degree of the numerator is one more than the degree of the denominator, which is the case here because 2 is obviously one more than 1. So what you're going to do to find that slant asymptote is actually do this division here. I'm going to, over here to the side, divide x into x squared minus 9. And I probably should have put a placeholder there. Let me put that in there. X squared plus 0x minus 9. And then, as we know, we say x times what gives me x squared? Well, that's just x. So that gives you an x squared here. Subtract, you get 0. Then you have 0x minus 9. Well, x doesn't go into 0x. That would just be plus 0. And then this negative 9 here would be the remainder. So in other words, we're saying that this fraction is the same thing as the quotient of x plus the remainder negative 9 over your original divisor x. X plus negative 9 over x. Now remember, when we're talking about end behavior, we're talking about what happens to the function when x gets very large and positive or as x gets very large and negative. And as we've talked about before, when you have a fraction like this, if x is getting very large, then you have negative 9 over a very large number, which will approach 0. And this is always what will happen when you do the division. The remainder part will approach 0 because now you'll have a fraction with a larger x value in the denominator than you have in the numerator. So this part's going to approach 0, and that's why I said in the previous slide here that you will ignore the remainder. That will always just approach 0 for larger and larger values of x. So what you are looking at for your slant asymptote is just this quotient here, which is the line y equals x. That's my slant asymptote on this one. So let's go ahead and graph that. And hopefully you're doing a better job with a straight edge or something, but that's about as good as I can do here. There are some other things that we can look at on this graph. Remember, wholes are where the numerator and denominator have common factors, which is not occurring here, so we're not going to have any wholes. Vertical asymptote, that's where the denominator is equal to 0, so that's going to be at x equals 0. Let's go ahead and draw that in. When there's a slant asymptote, there won't be a horizontal because remember, horizontals do not occur when the degree of the numerator is greater than the degree of the denominator. We could go ahead and find x and y intercepts as well. For x-intercepts, remember you see what makes the numerator 0. So if you have that x squared minus 9 equal to 0, that'd be x squared equals 9, meaning x is plus or minus 3. So we have x-intercepts at plus or minus 3, 0. You can go ahead and put those in place. Y-intercepts occur when you put in 0 in place of x. Of course, that can't happen here because you would be dividing by 0, so there are no y-intercepts. Also, you see there's a vertical asymptote on the y-axis, therefore the graph is not going to intersect the y-axis. And we can do the domain and range here in a second. So from there, you would just plot a few more points if you wanted to, or you can just look at these asymptotes and figure out the behavior. You know that the graph is never going to cross this y-axis because there is a vertical asymptote there. So it's going to approach the y-axis this way. And the end behavior, we saw that for bigger and bigger values of x, it's just going to approach this y equals x. So it's going to come out like this. Same thing over here on the left, and your graph looks something like that. Domain, what x values are being used here? You always have to exclude wherever the vertical asymptotes are from the domain. So this is the set of all x's such that x does not equal 0. Range. Looks like all real numbers here, so I'll just put negative infinity to infinity. And so that's our first one with a slant asymptote. Okay, let's try the next one. This one's a little more complicated, but again, we notice that the degree of the numerator is greater than the degree of the denominator. So we know that there is going to be a slant asymptote. On this one, let's go ahead and factor the numerator and denominator. I probably should have done that over here as well, but this denominator was so simple that I knew there wasn't going to be a common factor. So here, let's do that step. So up top, I can factor out an x. That's the greatest common factor. And then you have x squared minus 1, which of course factors as x minus 1 times x plus 1. In the denominator, that factors as x minus 1 quantity squared. Or in other words, if you want to write it like this, x minus 1 times x minus 1. Now, in this one, you do see that these x minus 1's cancel here. So really, we just have x times x plus 1 over x minus 1. Now, one thing that we learned yesterday was the fact that wholes occur wherever the at the common zeros of the numerator and denominator, which we would think would be at x equals 1. However, this is sort of a weird case because there's another factor of x minus 1 down here in the denominator. So there's actually a vertical asymptote at x equals 1. So there wouldn't actually end up being a whole at x equals 1 because there's already a vertical asymptote there. So let's go ahead and put that vertical asymptote in. Now it's nice because we don't have to deal with this big equation that we started out with. We just now have this one over here that we've already simplified. Let's multiply that back out for purposes of dividing. We have x squared plus x over x minus 1. Slant asymptote, I need to do the long division here. So I'm going to divide x minus 1 into x squared plus x. So x times x gives me x squared. Now I take this x and multiply it by each of the terms of the divisor. And don't forget to subtract. This is the step where most people missed points on the quiz last week. So try to fix that problem. X squared minus x squared is 0. X minus negative x is 2x. And then x goes into 2x 2 times. And then you would have 2x minus 2 here, subtract that, and you're going to have a remainder of 2. But remember, as we talked about in the last problem, you just ignore the remainder anyway because it's going to be 2 over x minus 1, which will approach 0 for large values of x. So your slant asymptote is just the line y equals, x plus 2. Just looking at that quotient there. So we'll go ahead and graph that line. It's a line with a y-intercept of 2 and a slope of 1. Again, hopefully you're doing a better job of drawing those on paper. All right, so next I can find the x-intercepts. To find the x-intercepts, you just want to set your y value equal to 0, or in other words, you want to set your numerator equal to 0. So here, if I have x squared plus x equals 0, and I solve, that's x times x plus 1 equals 0. Therefore, x would be 0 and negative 1. So those are both x-intercepts, 0, 0, and negative 1, 0. The y-intercept is found by setting x equal to 0. If you put in 0 squared plus 0 over 0 minus 1, that's just 0. So 0, 0 is also the y-intercept. I already have that on my graph. Well, I can already tell what's happening over in this little portion because I know that the graph crosses the x-axis at these two locations, and I know that it's going to approach that vertical asymptote on the right and the slant one over on the left. So that part looks like that. We need to figure out what is also going on to the right of x equals 1. So I'm just going to plug in maybe x equals 2. So if I plug in x equals 2, finding f of 2, just going to plug it in again to this equation over here. That's 2 squared plus 2 over 2 minus 1. 6 divided by 1. So it's 6. So the point 2 comma 6 is on the graph. Right there. And again, you can kind of imagine, that the rest of it would go like this. If you want to plot more points, you can, but that's a good graph right there. Domain,